All right, and we are back. So let's look at our rubber elastic system and kind of describe what's essentially going on here. So initially, I have a polymer chain, a polymer network, and we are going to say that it's unstressed, and we have basically a large number of subchains, so segments between our cross-linking points. So we're going to assume we have a lot of these types of segments here, and each of these kind of segments or subchains, what we're going to call them. They can be again defined Gaussian, some unperturbed distance between our chains. So this distance here is going to be described on average as our R naught squared. So there's also going to be each of these subchains is going to have basically some molecular weight of our subchain, mx. So they're all going to have the same molecular weight. So this is going to be the assumption that we say. So so as you can kind of imagine, given some initial set of chains, the molecular weight of each subchain will decrease as the degree of cross-linking is increased. So again, we have to conserve mass and volume and all this other good stuff. Additionally, once we apply a force to this system, so once we start to deform this polymer network, we're going to have some new extended end-to-end distance, and we could invoke this affine deformation. So basically, again, deformation experienced by individual subchains is equivalent to the deformation of the whole network. So we could focus essentially just on this specific subchain and see how that changes, and that's going to be equivalent to the deformation described by the entire network. So we could relate, again, microscopic perturbations to dimensions to unperturbed dimensions. So we could essentially look at what is the extension ratio in each direction to find, between this kind of lengths. So I could look at these extension ratios in our kind of coordinate system, 1, 2, 3. So my extension ratio is just the length, again, once I pull it over its initial length. And again, initially they all have the same, assuming that your sample has, again, same L naught in all three directions. So we can then use these extension ratios and start to write the coordinates of each of an individual subchain. Again, affine deformation assumption. So we could relate these microscopic deformations to the deformation of the network overall as a whole. So we initially have our kind of, basically your subchain at a fixed point. This is kind of our R naught system here. And then we're going to deform it and bind it to some new coordinate system, R. So that's essentially what's happening here. And we can relate this new coordinate system to our old coordinate system via our, essentially our kind of this extension ratios, or basically these kind of alphas here, the extension ratios. So you can also see and relate that to your change in your end-to-end distances. So your new, again, origin minus your old coordinates. So that's your, basically the size of your polymer, and then the new dimensions as well. But again, because we are assuming that the network is incompressible, the total volume change has to be 0. So that relationship has to hold. So the extension from all of these, they must be equal to 1. So our volume, our change in volume is not, our volume is not changing. So that is essentially the key thing that's going on here.